You know, when you think about your phone, it really feels like magic, doesn't it? You tap a piece of glass and this whole world opens up. But the real magic, the thing that actually makes it all work, isn't the screen. It's what's happening underneath, at a scale so tiny it's almost impossible to imagine. And that's the world we're going to dive into today.
So here's the big question we're tackling. How in the world do you fit billions of microscopic, controllable switches inside a computer chip that's smaller than your fingernail? I mean, it sounds completely impossible, right? But the answer, believe it or not, starts with one of the most common materials on Earth, sand.
To really understand how we get from a grain of sand to a supercomputer, we first have to solve a really fundamental puzzle in material science. See, we need a material that lets us control the flow of electricity. We don't just want a simple on or off light switch, we need something much more subtle, something we can fine-tune with incredible precision.
So, in the world of electricity, you've pretty much got two extremes. On one side, you have your conductors, like a copper wire. Think of that like a wide-open, 6-lane highway where electrons can just zoom along freely. And on the other side, you've got insulators, like rubber. That's a total dead end, a blocked road. Nothing is getting through. The problem is, neither of those really gives us the control we're looking for.
And that brings us to our main character, silicon. You know, it's kind of the middle child of the electrical world. It's not a great conductor, but it's not a perfect insulator either. In its pure natural state, it's just kind of mediocre. So the question is, why is this one element the absolute foundation of our entire digital lives?
Well, here's the thing about silicon. An atom of silicon has 4 outer electrons. We call them valence electrons, and these are the ones that like to socialize. A silicon atom loves to form these super strong, stable bonds by sharing one of its 4 electrons with 4 of its neighbors. This creates this perfect, beautiful crystal structure. But that stability is also a big problem for us. All the electrons are locked tight in these bonds. They can't move around. And if electrons can't move, you don't have conductivity.
So, if pure silicon is so, boring, how do we make it useful? This is where the first real stroke of genius comes into play. The solution isn't to change the silicon itself. No, it's to intentionally introduce a few atomic troublemakers into the mix. This process is called doping.
Doping is just an incredible concept. I want you to think of it like adding a pinch of salt to a really bland dish. You add just a tiny amount of this other ingredient, this impurity, and it completely transforms the properties of the silicon. It takes it from meh to absolutely magnificent.
Okay, let's look at the first method, N-type doping. N for negative. Here we add an impurity like phosphorus, which has 5 outer electrons. Now remember, silicon only wants 4. So 4 of phosphorus's electrons pair up perfectly with the silicon neighbors. But that 5th electron is left over. It's an outsider, a free agent with nowhere to go. So it's free to roam around the crystal. And just like that, we've intentionally created a mobile negative charge.
Now, what if we do the exact opposite? For p-type doping, P for positive, we add an impurity that has only 3 outer electrons, like boron. So it tries to form those 4 bonds with its silicon neighbors, but it comes up 1 short. This creates an empty spot. We call it an electron hole. You can think of it like an empty seat on a park bench. An electron from a neighbor can jump into the hole, but that just leaves a new empty seat where it used to be. So the hole itself appears to move through the material, acting like a positive charge. So this is absolutely crucial. We've taken our one kind of boring silicon and we've created 2 completely distinct materials from it. We've got N-type, which has an excess of free electrons, and we've got P-type, which has a deficit of electrons, or what we call an excess of holes. This is the foundation for everything, and I mean everything that comes next.
Okay, so we have our 2 new materials. We have a block of N-type silicon and a block of P-type. Now, individually, they're pretty interesting. But the real magic, the part that changed the world, happens when you put them together.
The moment these 2 different types of silicon touch, something incredible happens almost instantly. All those free electrons on the N side, they look across the boundary and they see all of those empty holes on the P side, and they just can't resist. They immediately jump across to fill them up. This initial rush of electrons creates this tiny zone right at the junction that we call the depletion region. In this little area, all the free electrons have found holes, and they've basically canceled each other out. This creates a neutral, depleted zone that acts like an electric barrier, and it prevents any more electrons from just casually crossing over. It's like a little no man's land has formed right at the border, and for now, that border is closed.
But here's where we get control. If we apply a voltage in just the right way, what we call a forward bias, we can actually push the electrons in the holes toward that barrier, shrinking it until it disappears and letting current flow right through. But if we reverse the voltage, a reverse bias, we pull them away from each other, making the barrier even wider and stopping the current completely. We've just created a one-way street for electricity.
And this brilliant little device, this PN junction, has a name. It's called a diode, and it's the fundamental one-way valve that underpins everything from the LEDs in your TV to the solar panels on a roof. But its greatest trick is what happens when you combine two of them.
Because if one PN junction is a one-way valve, putting two of them back to back creates something with, well, with superpowers. This device is the transistor, and it is no exaggeration at all to say it's the most important invention of the 20th century.
Structurally, a transistor is actually pretty simple. It's just like a sandwich. You take two pieces of our N-type silicon and you stick a very, very thin slice of the P-type silicon right in the middle. This gives you three layers, which we call the emitter, the base, and the collector.
And this simple little sandwich structure gives the transistor two revolutionary abilities. First, it can act as an amplifier, taking a tiny weak signal and making it huge. Or second, and this is the one that's crucial for computers, it can act as an incredibly fast switch that we can turn on or off with just a tiny little tickle of electricity.
The absolute best way to understand this is the faucet analogy. I want you to picture a faucet. The emitter is the source of the water, in our case, electrons. The collector is the spout, where a huge flow of water can come out. And the base? Well, the base is the handle. A tiny, tiny turn on that handle can control the massive flow of water coming out of that spout.
And that's exactly what a transistor does. A tiny little electrical current that we apply to the base controls a much, much larger current that flows from the emitter to the collector. That's the principle of amplification. And it's also how it works as a switch. A little bit of current to the base turns the whole thing on. No current turns it off. Simple as that.
So let's just zoom out for a second. We started with a humble silicon atom, which on its own wasn't very useful. But by manipulating it with these really ingenious techniques, we've created something with the power to literally change the world.
And I really do mean literally. Just think about this for a second. The processor chip in the phone you might be holding in your hand right now contains over 15 billion of these tiny transistor switches. 15 billion! And each one of them is turning on and off millions of times every single second. It is absolutely staggering to think about. So let's just recap that incredible path we just took. We started with a single silicon atom. We learned how to dope it to give it a purpose. We combined those doped pieces to create a diode, that perfect one-way street for electricity. And from that, we built the transistor, the ultimate controllable switch. Our entire modern world is built on trillions and trillions of these tiny, perfect little switches.
You know, it all started by figuring out how to control the flow of electrons through a piece of purified sand. And it really leaves you at a pretty profound question. If this one fundamental discovery could build our entire modern world, what are we going to unlock with the next evolution of this technology?